very nice introduction to me. Yeah, that was yeah, it's my great honor to get a chance to give a talk at this webinar. So yeah, I'm like super excited to talk, whatever I want here, right? So yeah, the title is like towards resource efficient PIM unit. So basically, first let me introduce, myself and not myself, but my lab. So lab name is like Emerging Computing Lab. So what we do is we develop like dedicated hardware and software for sustainable progress in machine learning. So yeah, we not really doing the mainstream like electronics or like algorithm, but like we do like forward-looking, hardware and software for machine learning. So we do like both hardware and software. So the main topic is like digital geomorphic processor full stack. So we build like from like IC like hardware, and we build all this, like through this all, algorithm and software stack, so including, this like geomorphic process compiler and so on. So that's like the main topic. And also we do like this deep neural network computation accelerator design like PIM or like NPU. And also we do some like high level work like like optimization of test scheduler. And also we do like IP design for this PIM, processor. And also like software wise, we do lightweight tracking algorithm, which is working on CPUs because we are looking at edge arrays. And also we do this LLM, but which is like lightweight LLM, which is based on like novel like linear attention mechanism. So yeah, I have like 4 PhD students, 2 master students, and the work I'm going to talk about today will be done mainly by this Changmin and Chung-Seok. Okay, so my talk has like 2 parts, and the first part is like general overview on deep learning accelerators. So basically, I'm going to talk about like general strategies for deep learning acceleration, and like a very brief overview on various accelerators like CPU, GPU, NPU, and PIM. So like the detail can be seen in this like review paper we published it last year. And the second part is like this special function unit. But like everybody's talking about, this like GEM-M or like GEM-V acceleration and matrix multiplication acceleration. Yeah, that's like major workload of deep neural network, but also, you know, like the lot of models include nonlinear functions like activation or normalization. The point is that they should be done on the same chip as this major workload accelerator. Otherwise, you're not really gaining the like offloading the CPU. So that's the point, the second point of my talk. So I'm gonna talk about these like special function units mainly for nonlinear functions, So 2 parts. And the first one is like activation function approximation based on lookup table. And the second part is normalization function approximation, which is very often used in like LLM, which is based on transformer. All right, so I think everybody knows that deep neural networks become very like heavier. So let me talk about deep neural network in terms of complexity. And mostly these days, because of this LLM, the complexity is like growing exponentially, as you can see. The y-axis is like the log scale. So like both like memory and also this processing, they become really heavy. So that's a general trend. So not really sure about the audience. So let me talk about something really basic. It's about the complexity. So this is like simple, like dense layers, like fully connecting networks. So which has like 4 layers, the first, second, and third, and the final layer. And there is like full connection. So you can define like weight matrix. If the first layer has N1 node and the second layer has N2 nodes, and you can define the weight matrix, for the first layer, which is N2 by N1, all right? The same holds for the, the second layer, and also the same holds for the last layer, like this, right? So let me talk about the space complexity. Space complexity is like, how much memory you basically need to implement this model on your hardware. So you can simply just count the size of the model and basically, the size of the data you basically need to put on your memory to play with this model. So, given that we have 4 layers, and each layer has like N1, N2, N3, and 4 node. So it depends on the data format. But if you use like brain float, BF16, you just the same like data format for weight and activation. Then let's say we have like B, which is the size of a single data. So we have like total N1, N2, N3, and 4. You all add up, then that's the space complexity for the activation functions. And also you got to think about the space complexity for all the weight, But, the weight has the complexity of N squared. So the weight is pretty heavy. So this is just a simple example. You have 10,000, 10,000, 10,000, 10,000 linear layers. And if you just count the space complexity, that is about this. So what you can see that mainly the weight is like dictating the total space complexity, all right? So what about the operation? The operation is like, the main operation is like this, matrix and vector, the multiplication. If you don't think about a batch, so let me talk about just a single batch, operation. So you got a weight matrix, which is like for the first layer, which is N2 by N1, and you have X, which is the input to the network, let's say, which is a vector, like this. So what you do is basically the multiplication of this matrix and vector. So just think about, the total input to the first node of the second layer. That is the result of inner product of this first row of the weight matrix and this vector. So this is inner product, which is a scalar value, is the input to this node, right? So we say this is a single MAC operation. So you multiply this, x1 and the weight element w11, and you accumulate it to like 0. So this is a single, the basic operation, which is MAC, one MAC, then you have to repeat it, right? So how many MAC operations you basically need for this inner product of this row and this column, which is like N1 by N2, right? And then of course you have this activation, which is nonlinear operation. So the number of nonlinear operations for this second layer is simply just N2. So the same as space complexity, total time complexity for this, the first layer operation is like this, right? So you can see that also for the same model, this model, you can tell the time complexity is this much. So the total time complexity is determined by, this MAC operation, which is a result of, the matrix, weight matrix and the input vector. So the point is that if you accelerate deep learning operation, is basically you accelerate, this like so-called like GenV operation, which is the multiplication of this matrix and vector. Or if you think about batch, and that is, multiplication of matrix and matrix. So that's a general strategy. You have to accelerate this, the MAC operation, then you can overall speed up the total computation. So, like in your network, it looks pretty complicated, but you can basically classify 2 different types of layers. The first is like dense layer, which is a linear layer, or like fully connected layer. So you can define, if you forget about batch, you can think about the input is a vector. Let's say you have M nodes. So the dimension of input X is like M. And let's say you have N nodes in the output layer. So you can define the weight matrix, which is N by M, right? And for this like dense layer operation, think about the number of floating point operation, which is basically the MAC operation, which is M by N, in fact, right? Which is, I just explained in the previous page, right? And how many weights do you need for this operation? that means how many weights the weight matrix, include. That is, I told you that the size of weight is n by m, so there are total mn weight. So think about the ratio of number of floating point operation per number of weight. That is exactly 1. So that means for dense layer, you load one weight and you do the operation just once. Okay, that is like defining feature of this dense layer. But what about convolution layer? Convolution layer is a little bit, like different from this dense layer. So I assume that you are familiar with this convolution layer. So just simple, just this like 2D like convolution using this like 4D tensor, and you have a 3D feature map, and the result is 3D feature map as well. So if you count just the number of floating point operation for this convolution layer, you have this much operations. Then how many weights do you need for this operation? That is actually the size of this like 4D tensor, rank 4 tensor. So then you can calculate the same ratio of the number of floating points to number of weights that is not 1, but that is H prime, W prime. H prime, W prime, they are the height and width of the output feature map, which is not 1, which is, it can be large depending on the tensor shape, all right? So that is like a very different feature, from the dense layer. All right, so let me talk about this like computer architecture. This is very simple, like MIPS data path. Okay, so I assume that you know a little bit of this computer architecture. So this is a simple MIPS architecture. You have this ALU, which is doing this arithmetic, like logical operation. You can do like integer or floating point as well, because modern CPUs have this floating point, ALU. So the thing is, this ALU does arithmetic operation, but mostly like binary like operations. So that means like each operation needs 2 operands, right? They should be located in this register, which is register file, right? So the question is, where are they coming from? They are from this memory, in fact, data memory in the computer. So how it works is you have to first load 2 operand using this instruction, like load store operation, which are like memory operation. So you load one operand, which is located in the memory, to the register F1, and you have to load another data which is located in the memory to another register, which is F2. And then you do this, floating point operation. In this case, that is like multiplication. And you put the result in the register F3, and then you have to put it in the memory, and you have to repeat it. This is how the CPU works, right? The thing is, in deep neural network, the operation, the major operation is like math, right? Not just single multiplication, but you have to accumulate it to a buffer. But the thing is, the CPU is for like the very versatile. You can use bunch of different instructions on bunch of different data, right? That's the beauty of CPU. But that is not really efficient for deep learning operation, because the types of instructions you actually need for deep learning operation, not so many. I told you that the major operation is back, so that's massive. So you have to accelerate the back operation. But thing is, you don't need many instructions, but instead you need a huge amount of data, right? So if you use this CPU, I told you CPU is good, but not for deep learning. So how you can really accelerate these deep learning operations using the hardware other than CPU, then you have to offload those operations from CPU, and you have to use different, hardware. So that is basically what I'm going to talk about today. Okay, and again, let me talk about these instructions. Load data and do operation, and put the data back to the memory. So the thing is, either you have to accelerate this, like load store operation to accelerate, this like deep learning operation, or you have to accelerate this, multiplication. Okay. So, this is like loop line analysis, which is not very precise, but it can give you very, very good insight on, this deep learning accelerators for specific type. So this x-axis is like arithmetic intensity, which is number of operations per number of bytes. That is actually this, So this corresponds to arithmetic intensity. So for dense layer, the intensity is pretty low because that's one. So you load one data, which is weight, and you do operation using that weight, right? But like convolution, you load one weight and you do multiple operations, right? So when the arithmetic intensity is high, for example, it is located here. So that's a case of convolution, right? Because like convolution, like I told you, you load one weight and you do multiple operations using the single weight, right? So in that case, the total, the speed of the operation is determined by the parallelism of your hardware. Because this is a case for just a single operation, but what if you can do like multiplication and addition, at the same time using multiple, parallel, processing engine. So you can actually speed up, you can increase the throughput of the operation, right? So if that's the case, the total, performance is determined by the hardware's like peak, like operation speed, right? That is so-called a compute bound model. Okay, but what if you have some model which has very low arithmetic intensity? So you load one data in extreme case, like dense layer, you load one weight and you do a single operation. If that's the case, the arithmetic intensity is extremely low. Then what is actually determining the total, the performance of the hardware is actually not the peak performance, but the memory bandwidth. So that's exactly the case. Like you have a like water tank, and you process the water, stayed in the water tank, but you first have to fill the water tank, then you process the water, right? But what if you have to fill the tank first, and small amount of water you use to process the water, then the overall speed of the whole operation will be determined by the rate of the filling the tank with the water, right? So that is so-called, this memory bound model when the arithmetic intensity is low, but arithmetic intensity is high, that is so-called compute bound model. So depending on the model, you have to choose a proper, the acceleration strategy. All right, so the minimal change is you use basically CPU, but you still want to accelerate the deep learning operation. That was done like by like major like CPU chip maker like Intel. So the strategy is like you have to bring all the data from the DRAM through all these cache memories, and you have to bring it to data path. But the idea is that you don't want to do it. Instead, you want to do some like basic operation in the cache, like last level cache. In that way, you don't have to move the data through the cache, right? But still, you can do some operation. It's good idea, right? But thing is, the size of cache memory is limited, right? But these days, the trend of the deep neural network is getting bigger and bigger. But absolutely, this cache memory size is not big enough, all right? So, but when it comes to like small model, it can be effective, right? So the mainstream accelerator is GPU, so-called like GPGPU. Like GPGPU basically have like CUDA cores, but these days GPGPUs have a lot of tensor cores as well. So they are getting similar to NPU these days. But let me just talk about like CUDA cores. CUDA cores is like you have like streaming processors, but you have many processors. So you can basically do like massive parallel operation, right? So on top of it, so these like high-end GPUs have HBM, which has like very high bandwidth. So this is like just a schematic of like roof-line analysis for like bunch of different accelerators. So when it comes to GPU, like GPU has massive parallelism, and also it has a very high peak performance of each core. So it's the peak operation performance is very high at the same time. So in this regime, which is dictated by memory bandwidth, is also high because like high-end GPUs use like high speed, the memory like the HBM or GDDR6 these days, right? So that's the beauty of like GPU. It also, has like very rich legacy, not just hardware or software as well. It has like CUDA core, also, like all these like mainstream libraries like PyTorch or like TensorFlow, they are basically based on this CUDA core. So, it has this rich legacy. So what about NPU? NPU is like dedicated to the specific operation. Like CUDA core is like versatile. You can do a bunch of different, operations, but a single instruction. You can apply that single instruction to multiple data. But like NPU is like dedicated to that specific operation, right? So that specific operation is, so of course, either matrix multiplication or matrix vector multiplication, right? So the thing is, it has multiple cores. So in each core, you have a multiple. In each core, you can have a process like engine, right? It has like buffer and register. So the thing is, there are a bunch of different like designs of NPU, but NPU is just like general, the name of the hardware like dedicated to certain like your, like operation. So it was first coined by this guy back in like 2012, long ago, right? More than 13 years ago. But this NPU is quite effective. And also, like I told you, if like GPUs these days have like tensor cores, they are basically similar to NPU. That's basically dedicated to matrix, or matrix vector multiplication. Okay, that's NPU. And what about like PIM? The NPU is still processor. Remember, NPU is not memory, that is processor to offload the major workload from the CPU. But like PIM it's a memory basically. So that this is a schematic. You have like memory banks, in a bank, you have a certain like memory array, but you have these like processors nearby or in the memory your array. So for example, like near data like processing or something, that is basically like digital approach. You have the memory bank and you have processing elements around your memory bank so that you don't have to move data a lot. Still, you can process the data within, this memory bank. That is like near data processing or something. But like this analog PIM or analog CIM, that is like you merge this memory domain and this like processing element. So you can play with a lot of like this like analog like operation, which is very effective. But you at the same time you have to think about like this like all this like peripheral circuit and also like reliability of the operation though. But that is basically like PIM. So PIM is basically the memory, it's not a processor. So that's basically like PIM. So let me briefly summarize, these all different, the hardwares using this roofline model. So CPU, CPU has very limited, parallelism because still, CPUs these days have multiple cores, but number of cores is not large, right? So the parallelism is limited. And also the CPU itself, you don't really use high bandwidth memory. So in this like loop-line model, the peak performance is pretty low, and also the bandwidth is pretty low as well. So it's not a really perfect solution to deep learning acceleration. Like GPU is good. Like GPU has a very high peak performance, and also if you use high bandwidth memory, it can have very high memory bandwidth. So you can basically increase the regime of this peak performance with respect to this arithmetic intensity, right? So NPU has a massive parallelism because you have multiple processing elements. So you can have pretty high peak, operation. But if you don't use high bandwidth, memory, the bandwidth is pretty limited. So PIM, PIM is that you can't really define the bandwidth because you do the processing in the memory, within the memory, right? So that effectively it has, the bandwidth itself is not meaningful anymore, right? But still, I just drew, this the bandwidth regime, compute bound, regime because to compare. But the peak performance is limited if you have PIM. So let me talk about the mainstream PIM, which is like DRAM PIM. But this is not analog, but this like near data processing based on DRAM. That's basically DRAM, but you have processing element within DRAM, all right? So the point is that you have to make the DRAM and the processing element on the same die using the same process, right? But the DRAM process is not fully CMOS compatible, right? So if you build processing element using, this DRAM, process, the performance is pretty low. That is the discount of the DRAM based PIM. So, but anyway, and also this because that's memory, so the parallelism is also limited. It's not like NPU or GPU, right? It's limited. So this is like short summary. The good thing about PIM is that when it comes to LLM, LLM is based on this dense layer. So it's more, it's likely a memory bound model. So that's why these days everybody's crazy about this high bandwidth memory, right? When it comes to GPU. But if you use PIM, you can basically forget about the bandwidth, right? So the PIM can be a good solution to LLM acceleration because you basically need at least like DRAM anyway. So you put all the data in the DRAM, you process the data in the DRAM, and then it can be a good solution, right? But the point is that other than the linear operation, which is major workload though, right? What about all these nonlinear operations? The thing is, if they should be done, the off chip or like CPU or some other devices, that you are basically losing the advantage of this PIM. So that is actually the second part of my talk. So the point is that they should be done on the same chip as the PIM, right? So take a look at this. This is the basic like transformer architecture. So the architecture itself is pretty simple. So you have when it comes to just a decoder only, the transformer. So you have input, you have positional encoding, and you have this like attention, matrix, and then you have this like softmax operation, which is nonlinear operation. You also have this normalization. In case of traditional transformer, they used L2 or normalization, which is based, that is like layer normalization. But these days, this RMS normalization. Anyway, both are nonlinear operation. And you have, again, here, normalization. Also, you have softmax, and you have normalization, and here you have activation function. But thing is, these are minor in terms of the amount of the operation. If you compare those with the major workload, which is matrix or matrix vector multiplication, but you need them, right? But the thing is, this is just a simple schematic. Let's think of just like PIM. You have this kind of like PIM. You have a memory, and you have processing element, and you have buffer, and you have DRAM, right? But thing is, this PIM is for offloading like member from the CPU. So what if this PIM is only doing like member, like matrix multiplication or something like that? What would happen? So you do the operation, you have sent all the data to DRAM, right? And you need some other device which is also doing this nonlinear operation. You have to bring the data back to DRAM, and then you have to put the data back to PIM, and you have to do the same operation. So what about those data transfer? So take a look at this right part of this slide. So this blue is like this so-called like optimal scheduler we recently working on. So even if you optimize the data traffic from this PIM or like MPU can be like universal, and DRAM, and let's say this hardware is only dedicated to this memo. So basically you need to move a lot of data through DRAM. And then what if you can't do that nonlinear operation on the same chip as this like memo? You're basically losing the advantage of this PIM because you have to transfer a lot of data. But the philosophy of PIM is actually minimize the data transfer, right? So yeah, that's clear. You have to do all these like nonlinear operations on the same die as the PIM or something. All right. So yeah, that's the main idea. The PIM these days, not only this memo accelerator, but also should include all these nonlinear functions. But when it comes to LLM, nonlinear functions, you need not a lot. You need just a few nonlinear operations. So that's it, basically. Okay. So yeah, that is the second part of my talk. So you got to think about special function unit, which is for nonlinear operations or functions. So in this talk, I'm going to talk about two different, nonlinear functions. The first one is activation, function, and the second is normalization. So let me talk about this activation like approximation. So there are a bunch of different strategies, but you have to remember that the PIM, the computing resource or the hardware resource is limited, right? But when it comes to a DRAM-based PIM, like I told you, that should be basically memory. You cannot make it like CPU, which is very versatile, right? So what I mean is the resource is strictly limited, but nevertheless, you need to implement these operations. So the thing is then you have to make it very efficient. Otherwise, it's not going to work. So this lookup table based approximation method can be very useful in this sense. So there are a bunch of exponential function based nonlinear operations, activation functions like GALU, the sigmoid, and swish, and hyperbolic tangent. And these days, this swish is very widely used in the like LLM, right? And the same holds for GALU. So, what about these functions? How can you implement these operations based on lookup table? So very straightforward idea is that you have a certain range of the input, right? When it comes to swish, you have a certain range, let's say from -5 to +5, and you simply just like uniformly like binning the whole input, and you can build a lookup table in this way, right? So the point is that, I mean, it may work, but the thing is, take a look at this right hand part, I mean, when the input is positive. So the smaller the bin size, the preciser the output, right? So it's good to have a smaller bin on the right hand side. But what about the left hand side? The left hand side, when the input is large, the negative side, it's almost zero, right? So it's good if you have the uniform distribution. But on the right hand side, the smaller the bin size, the better in terms of precision. But left hand, it doesn't matter. So in this way, you have a certain like redundant use of memory, right, for this lookup table, right? So we came up with the idea is that we can build the lookup table, which is not for just like uniformly distributing delta x along the input, but instead we can use the gradient, So we can use like gradient based the organization of a lookup table. So the idea is very simple. So if you have this nonlinear function like this, it has like this kind of like sigmoid behavior. If you have a like certain value, let's say xi, and you have xi plus one, and you can define like like this x bar. So the function value at x bar, if you know the gradient of let's like x tilde, let me define x tilde, somewhere between xi and xi plus one, and this x bar, which is here, and if you know the function value at xi, if you have a proper f prime, which is a gradient of f with respect to x, you can basically approximate it in a very, very, very precise way. So the idea is that rather than just organizing lookup table in this way, we can organize a lookup table in this way. We have a xi and xi plus one. So you have this lookup table column for x, and this is like corresponding y value, like function value. And here you have a gradient value at not necessarily at this point, but some point between this and xi, all right? So the basic idea is that you have a let me talk about it. So let me skip all this math. The detail you can read the paper. So the idea is that you have this like the gradient value, which is f prime, like x tilde. Let's say this is a x bar, which is the x value. We want to calculate this function value at this point, right? But like I told you, we use the gradient. Let's say we define the gradient value at, let's say here, right? If you know the exact gradient value at this slope, if you know this slope, right, this one, and this xi value and the function value at xi, which is fxi, so using this slope value, you can calculate function value at here exactly. But thing is how you can build the gradient value, which is not exactly here, not here, but it should be here, right? So if the function is like continuous and differentiable, you can basically define x tilde somewhere between xi and x bar, in between this, then you can have a like x tilde. The gradient value at this point is actually the gradient value you want to know, which is this, right? So we can define the gradient at this point, And of course, there is like approximation error, right? Because we are not going to use the gradient value at exactly at this point because we don't know this point exactly, right? So instead, we have a like approximation error. So let's say you approximate it this way because this is not precise. You have this much approximation error, right? And you have this maximum error is when this x tilde is the same as xi. That is a maximum error. So the point is that we allow this much error. If that error is not large, we can allow this much error, not a problem because this is anyway approximation, right? So this is like the error, which is like allowed, right? So with this allowed approximation error, we can build the gradient value this way, okay? So, and then how we can build the lookup table. So what we have is just this like the error value, which is allowed, right? So we build the lookup table from the top to the bottom. So we increase the input and then we can figure out what is the z, which is x value, which has that much tolerable or allowed error value, right? So in that way, you can fill the lookup table from the top to the bottom, okay? So let me skip it because time is limited, right? So let me skip the detail. So the thing is, in this way, you can build and how you can figure out what C value is. So you can use this Newton-Raphson approximation. So in that way, you can figure out, where is the next input value, which has that tolerable like error value. So you can repeat it. So repeat it, and then you can basically, oh, sorry, let me skip it. You can fill the lookup table, and also, so a lot of these like activation functions, either they are like symmetric or their gradient function is symmetric, right? So because of that, you don't actually have to have all these lookup table for all this input range. Instead, you can have just a positive, the lookup table for just positive input, right? Then you can build the whole, the activation function for all these different, input, no matter what, it's negative or zero or positive, right? Cool. All right. So yeah, you build the lookup table. All right. So what about you have this x, any like random x between the negative, bound and positive bound, you have a random x value, then how you can search for that specific, x value and y value and the gradient value. So to this end, you have the scaling factor. You have x, which is input. You have this scaling factor, which is a power of 2, right? And that integer part corresponds to the, the address of the column you are interested in. So you can only search for certain range of the input. So that way you don't need to search for search for the value in the whole lookup table, right? So in that way, you can accelerate this search, and also you can reduce the search domain, right? So in fact, we have a scaling factor of 8, right? And then they can take a look at it. Like average search range is not large, that is about between like 1 or 2 or something, right? Right. So how we can implement it? So the implementation is pretty simple. We have basically like 3 lookup tables, x, y, and gradient value, and we have this scaling logic. So using that scaling logic, we can take the integer part and we can address, all the gradient and x and y value from this lookup table, and you simply just do the calculation, which is just a multiplication and addition. And then you can get the data value. Let me skip it. All right. So what about the precision? Precision is pretty good. So we tested all these 4 different activation functions and we varied the data format from floating point 32, floating point 16, and brain float 16, right? And then we compared the error. So the error is pretty low. So if you compare the same strategy, but using this uniform X, but the lookup table size the same as our gradient-based lookup table. We have a pretty high, low, error, which has a high precision, which is good, right? And we built the macro and we estimated the power of the system, right? And we have this the breakdown of the power and the area of this our macro for this activation function approximation. Okay. So yeah, let me move on to the last part, which is like normalization function approximation. So like layer normalization or like RMS normalization, they are very often used in LLM, all right? So that is basically like when it comes to layer normalization, you have a like certain like embedding, which is a vector. And what you have to do is you have to first calculate the mean, and you have to shift the vector by the mean, and you have to calculate this like variance, and you finally get this like normalized, the output, and you have to address this, this scaling and shift value as well. So this is a layer normalization, right? So the point is that, you can see here you have a square root operation and also you have division, right? But the thing is, like I told you, this like PIM, like when it comes to computation, the resource is very limited, right? But if you have like this square root accelerator and you have this division operator, you can do it, but but they can be complicated, right? So here the main idea is that how you can do this normalization without division operation and without square root operation. That is basic motivation of our work. Okay, so this is a basic step which I just talked about. You gotta calculate the mean of a vector, and you have to shift the vector by the mean, and you have to calculate this the variance, and then you have to consider the scaling and shift to finalize this layer normalization, right? But our main kind of contribution is that we do this like L2 normalization without division and square root operation. That's basic idea. How we can do it? We make use of dynamics of like system. So think about like this is a hyperdimensional space. You have a vector. So, but the vector system is like dynamic. So there is like dy dt system. That means unless this is zero, this is dynamic system. It has a certain function. The thing is, we designed this dynamic system in a way that this system has a so-called fixed point. So as time goes by, let's say this system moves towards this fixed point, and let's say we design the system such that this fixed point is given by this. So this is actually the R2 normalization, right? So that is our strategy. So what's remaining is that we have to properly design our dynamic system. So this is quite like empirical. So we can design our dynamic system in this way. So, this is a dynamic system. Let's say K, K is, the inner product of input Y and like Y tiered, that is the inner product result is K, okay? So you have alpha, which is just a positive constant. So what about this dynamic system? If you have this dynamic system, you can see the proof of this dynamic system that it has this fixed point which corresponds to this R2 like normalized vector, which is y tiered infinite, that point. So if you just keep solving this dynamic system, you end up being at this the fixed point. That's basic idea. All right, good. So how we design our dynamic system, then we have to implement it. How we can do it. It looks pretty complicated, right? But the thing is, we basically talk about this step two. You do this R2 normalization, and the fixed point is this value. So you can get it without using any square root or division operation. Okay, so but this is the y dimension. Think about the embedding in an LLM. The size is like the larger than 1,000 very often, right? So the calculation can be very costly. But the good thing is that if you initialize which is y tilde, which is the result of this, the operation, if you design it the way that it initially aligned with the initial vector y, and then you can think of y tilde, which is the scalar multiple of input y, right? And then what you can do is, if you do so, the system actually becomes just 1D system because you have that coefficient. Right here, I use the coefficient like A, right? Because y tilde aligns with y value. So y tilde is A, which is scalar, multiplied by y, right? So the system becomes a 1D system, which is very simple now. So if you just arrange this equation in terms of A, you actually just have this equation. So A is just a scalar value. You can just update A value a few times, then you can let your system stay at this, the fixed point. That's basic idea. Okay, so the algorithm is pretty simple, right? For this L2 normalization. So you need to calculate this like mean value first, and you have to shift the vector. And here you have to calculate this like inner product of y with itself, that is m, but you have to do it just once, right? But you have this while loop, and you basically repeat it. You have basically repeat this operation until you reach that fixed point, and you have this steady state a value, and then this is actually the R2 normalized vector, right? Y hat. Okay, so let me just go. All right, and the what matters is like this iteration, right? So because this iteration is serial, so it's time consuming. So good thing is like if you have a proper initial point and the initial point is very close to that, the potentially the steady state point, and then you can use just a few iteration steps so that you can speed up the operation. But luckily we roughly know where that the steady state a value is, because if data is given in this floating point format, so you can basically see that because m, which is like this the inner product of y with itself, you basically know the exponent value of that, and simply a naught is like inverse. So you can take that like inverse exponential point, like exponent of this the square of this y. So you can take that a naught as an initial point. Then if you do so, you can reach that steady state point within just 3 steps or something, which is good. Okay. So this is just like the implementation using FPGA. The logic is pretty straightforward. We basically do all these the steps I just talked about. Okay. So let me skip it because it's nothing really special, right? So yeah, so we compare the performance of this our approximation with like FISR, which is fast inverse square root algorithm. So we can really see that if you compare our algorithm with this FISR, the precision is quite high compared to FISR. And also, like I told you, because of proper use of that like initial point selection, we can see the error value with respect to iteration step. Even you use like floating point 32, you can reach the steady state after like 6 iteration. Otherwise, you can have that fixed point within like 4 steps or something, which is good. Okay, so the power and the area is extremely small because the most area and most power are consumed by the buffer, but that buffer is not only for this like normalization operation, but that can be a basic like register file for the whole macro. So it's not really used for this operation only. So if you consider that the core area and core power of this macro is extremely low. Okay, and we applied that our normalization algorithm to this LLM, quite small size LLM, and you see that the performance degradation is negligible, right? Which is good. All right, so basically that's it. And let me briefly summarize, my talk. And the first part of my talk, I gave a very brief overview on deep learning accelerators and like CPU and GPU and NPU and PIM. So the key point is that the fast load store with high bandwidth memory or near memory operation, and you need like massive parallelism to accelerate these deep learning operations, or like maybe pipeline multiple instruction devices like what if I have this special function unit together with this PIM on the same chip, you don't really need to depend on just single instruction, multiple thread, but instead you can play with this like optimal scheduling. So the partial data can be processed. So in this way, you can do sort of like pipelining of this operation. And the second part is like the key point is that you need special function unit definitely, right? So yeah, you need to deploy this kind of like special function unit for nonlinear operation on the same die as accelerator, right? So yeah, that's it. Thank you very much for your attention.
Right. Thank you very much, Dusek.
Subscribe the channel to get the instant updates on our webinars.